Today, we're going to start with questions. Emma. Sure. All right, so the directions on 7 ask 0, 1, or determine if there's 0, 1, or 2 triangles possible for the problem. So I'll start by just drawing a picture and labeling it. So first thing I want to do, now that I've drawn and labeled my picture, is determine what situation I'm in. What situation is this? Anybody. Doesn't have to be just you, Emma. This is side-side angle. Yep. Very good. Again, what we're looking for in an SSA situation is one of the two sides is not part of the given angle. Okay, in an SSA situation, it's either going to be that for sure one triangle, or we're going to have to figure out whether it's 0, 1, or 2. So the first thing we're going to look at is the size of the given angle. So that's angle P. Is angle P acute, right, or obtuse? Acute. Okay. And then we have to compare the side opposite our given angle, which is side P, with the other given side, which is side Q. Is P smaller than Q, equal to Q, or bigger than Q? Smaller than Q. So this is the case where we have 0, 1, or 2 triangles possible. So we have to do that further step to determine which one of these it's going to be 0, 1, or 2 triangles. We take the bigger side, we multiply it by the sine of the given angle, and then divide by the smaller side. And then that number is going to tell us what's going on. So I do that, I got 1.05-ish. Okay there? And if this number is bigger than 1, we get 0 triangles. If that number was equal to 1, it would be 1 triangle. And if it was less than 1, we'd have 2 triangles. Mackenzie. Yes, sure. So 14 says we can make 2 triangles. So the directions have already told us we're in a 2 triangle situation. So I can skip a bunch of those steps and go right into the solving part, because we've already been told what's going on. So again, I always start with drawing and labeling my picture here. So I'm going to make a space to write my answers for triangle 1 and for triangle 2. So the given information is a part of both triangle 1 and triangle 2. And in triangle 1 and triangle 2, we're going to have to be finding angle A, side C, and angle C. And likewise, we're going to be finding those in triangle 2 as well. To differentiate between those two, I'm going to use subscripts to indicate what triangle I'm finding that angle in. Cool. So now I'm going to make a space for my work. So I'm going to make a space for triangle 1 and for triangle 2, just so I can stay organized. Typically, the way I like to do this is to do all of triangle 1 first and then go all through triangle 2 second. So starting with triangle 1, I'm going to just solve this like a normal law of sines problem. So I notice that I have one pair of angle and opposite side given to me. And then I have one other situation where I know one of the two. So that's what I'm going to use to set up my law of sines. So I'm going to do sine B over B equals sine A over A. Oops, B is 10. Yep. I'll cross multiply, so that gives me 10 sine A equals 11 sine 57. Divide by sine 10, or I'm sorry, divide by 10. And then to get rid of that sign in front of the A, and really I guess we mean A1 here, sorry. We use sine inverse, right? So I'm going to go to my calculator now. So sine inverse of 11 sine 57 over 10. Again, what mode am I in? Degrees. How do I know? Because I'm working in degrees. So that was 6730. Now that I have angle A1, getting angle C is easy because I know two of the three angles, so I can just add those two together and subtract from 180. So 5570. So far, so good, Mac? Okay. And now that I know angle C, I can solve for side C using the law of sines again. So I'll do sine B over B equals sine of C1 over side C1. So we cross multiply and then divide by sine 57. And then we'll just go to our calculator.
Isn't it 67?
Ooh, is it 67?
Yeah.
Did I just copy it down? Well, why didn't you say something so much sooner? 14 is 57. Oh, 6730. Right, I have it there.
You changed it somewhere.
No, 57 is the angle B,
Oh, I see it. Never mind. Okay.
right?
Yeah, I got it.
I'm good? Okay.
Yeah.
I think I'm good. Again, if you think I messed something up, yeah, please speak up. Sometimes I will have made mistakes, but sometimes I don't. You know, it happens every once in a while. I get it right on the first time. Woo! So I get 985. All right. So that finishes up triangle 1. Now triangle 2. This piece is important. I probably didn't emphasize it enough the first time we talked about this, so please pay attention here. The order that I found my pieces in triangle 1 needs to be the same order I find the pieces in triangle 2. So I start off by finding angle A, then angle C, and then side C. I must do it in the same order for triangle 2. So to find angle A2, that's the first thing I need to do. That is the supplement of angle A1. And this is specifically the spot where you have to make sure you're doing stuff in the right order. So that's 112.70. Because if you tried to find angle C2 here first by looking at the complement, you will not be getting the right answers. You know what I mean, guys? And that's something where we did it this way, but I don't think I emphasized when we did the examples that like, no, you have to make sure you do it this way. I think we just always did it that way, and I probably didn't emphasize that it wasn't just me doing this conveniently, like just doing it the same way for the sake of doing it the same way, that it's really important we're doing it in that same order. So that's 1030 for angle C. And then I can set up side C2 the same way I did before, except I'm using angle C2 here instead of angle C1. And then I'm going to skip some of the algebra there, Mackenzie, and just go straight to what I'm typing into my calculator. That's okay, right? I figure if it's the same thing that we basically just wrote over there with a different number, that's probably okay. Oops. So I got 213. I guess I haven't been writing these down.
The second step,
Yes.
you took a. Hold on, I'm just trying to make sense of the second step compared to the first one. So you took the supplement of the. Or you looked for the supplement of the.
So what do you mean by the second step?
The second step of like triangle 2, where you took like 180 minus 57 degrees.
Minus 112.7? Yeah, just using the triangle sum theorem, right? There's 180 degrees in the triangle. So at that point, I knew the 57, I knew the 112. So I just subtracted from 180 to get the 1030.
But the 180 minus A1 equals angle. Show me that real quick. Like,
This,
yeah.
that's always your first step.
Oh, okay, gotcha.
That's just how you start triangle 2.
Okay.
But you have to make sure you're using the same angle that you started with triangle 1.
Okay.
So I can't start with angle C2 that way.
Right. Okay.
Has to
So
has
the
to
angle-
match
okay,
up.
So the angle you're doing will always be. Okay, that makes sense.
You have to find the
So once you
pieces in the
start with-
same order that in triangle 2 that you did in
Gotcha.
triangle 1.
Okay. Makes sense.
Yep. Drake, did that? You're good? You got your question answered? I know we kind of stumbled around and people jumped in, we added and subtracted, but just double check it. Mackenzie, you're happy with that?
Yeah.
Problem number 5 from worksheet 1. Is it another 2 triangle problem? You don't think so? Okay. I'm just giving you a hard time. I don't care if it's another 2 triangle problem. I'm just tired. Well, it's definitely an SSA problem. So again, we'll draw our picture and label the pieces. So observe this is an SSA. So the first thing I'm going to check is the given angle. That's acute. So that's the potentially worst place. So in the acute situation, either you get one triangle or you get that unknown 0, 1, 2 situation. So I'm going to compare the side opposite the given angle with the other given side. Since the side opposite is bigger than the other given, there's just one triangle possible. That's nice. So we'll just set up our law of sines problem. So I'm going to do sine of angle S over side S equals sine of angle U over side U. Cross multiply. Divide by 25. And then do the sine inverse. Feel good so far, Mac? Okay. So that's 1821. Now that I have this, I can find angle T. So 180 minus 23 minus 1821. Yowzer, we're going to have a big side and angle here, huh? What did I, oh, great googly moogly. Pressed the wrong button. No, oh yeah, that's still good. So 138.78. Still doing okay?
Yep.
All right. And then to finish this off, we need side T. So we'll go back to the law of sines. So we'll do sine of our newly discovered angle T over side T. Cross multiply and divide. I'm going to skip some algebra here. Everybody okay with the skipped algebra there?
Yep.
Again, you do a couple of these and then you realize like, hey, it's really kind of the same thing over and over and over again, the algebra. And I don't mind writing it out, but like if you guys are good with me not writing it out, it just like, you know, saves a minute or something. So 4216. So there's my answers.
Yeah, that's like a column. It's not that. It's like that.
Sure. Okay. So there's two situations. If the given angle is greater than or equal to 90 degrees, so if it's obtuse or right, and the side opposite the given angle is the bigger side, oh, let's say smaller. I'm going to say smaller. Actually, no, I do want to say bigger. I lied. That's going to be the easiest way to say that. Is the bigger side, then one triangle is possible. Otherwise, 0 triangles are possible. So if the two sides were equal, or the opposite, or the side opposite the given angle was the smaller, no triangles. Okay, so that covered case 1 and 2. All the different bullet points in it are covered in that little summary, right?
Okay, so if it's bigger than 90, then it's 0 triangles.
If it's bigger than or equal to 90 degrees, the given angle, you're either going to get 0 triangles or 1 triangle. All you have to do is check the side opposite the given angle and see if it's the biggest one.
Okay.
If it's the biggest one, there's 1. Otherwise, it's 0.
Okay.
Okay. The other situation is if that given angle is acute and the side opposite, opposite is spelled that way. The given angle is the bigger, we're going to say the smaller side. Then this is the 0, 1, or 2 triangles are possible. So you have to do that extra analysis there. Otherwise, 1 triangle is possible.
Okay. And if it's 90 degrees, then is there just 1 triangle?
90 degrees is covered. If the angle is 90 degrees, it's covered in that case.
Okay.
Right? If the angle is greater than or equal to 90 degrees,
yeah,
same rules up in the first one. Okay, so this is basically what I took. I just took the case 1, 2, and 3 and summarized them into a statement.
Okay.
Right? This is the same information that we had written down. We've just synthesized it into something that's maybe easier to remember, rather than like, if AB is greater than BC, then, you know, like that got to be pretty alphabet soupy. This is manageable. This feels much more manageable, right? In general, this is what you'd want to be doing when you're given like rules for any kind of a technical class. Is like the way the rule was stated was hyper-specific, but not very practical, right? The first thing I'd want to be doing as a student is like, okay, how can I synthesize this into a way that's easier to remember, that's practical for what I'm going to be using it to do? I don't need to be super specific and like give these things always names, because the names of the triangles are always going to be different, or most of the time are going to be different. Can I just write it as like, you know, angle and opposite and then other, and, you know, Mackenzie, does that help?
Yeah.
Paul, you good with that?
I get it, yeah.
Okay. And that's probably like an easier way of managing like how to remember that stuff. Because again, it's important that you remember that. Like that's the hardest part, right? Once you've got the thing figured out, doing the algebra is rather straightforward. But I think that's probably easier to memorize rather than like this, all the cases that we gave the first time through, right? Okay. Other questions from you guys?
Are we doing law of cosines?
We've done it. We did it last time. Yeah.
I just forgot what that's.
Yeah, those are the side angle side and side 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 situations. I thought you had a question that you're going to ask about those.
Side. One of those.
Yeah, do you got one in particular you want to do, or you just want me to make something up?
Side.
Okay. I'll just make something up then.
Sounds good.
Okay. So let's start by drawing a picture. And then labeling it. Okay, quite obviously this is a side situation, so we should be using the law of cosines. But before we dive into using the law of cosines, what do we need to check first? If there's even a triangle possible, right? What's the check here that we need to do? We need to check to make sure the sum of the two legs is greater than the hypotenuse. So that's certainly true, right? 6 plus 7 is greater than 9. Great. So now we need to start solving. Since I know all three sides, realistically I could solve all three angles, correct? What one should I start with, though? Yes.
Side.
The largest angle, which is across from the biggest side. So I want to start by finding angle B in this case. So using the law of cosines, I'll write b squared is equal to a squared plus c squared minus 2ac times cosine b. So I need to solve for b. So I'm going to subtract 6 squared from both sides, and then subtract 7 squared from both sides.
And how is cosine? No, because it's big axis.
These match.
Yeah.
That's the way I remember it. Then I need to divide by 2 times 6 times, or negative 2 times 6 times 7. Don't drop that negative. That'd be a big problem. You'll get yourself some bonkers answers that way. So far, so good.
Yeah.
And then cosine inverse. And this is a situation where if you haven't been using the fraction command on your calculator, you'll get severely punished because it's tough to get the parentheses right for your calculator to do the order of operations here in the way that you really want them to. So, oops. So I would highly recommend making sure that I'm using that fraction command on a problem like this. So 8727 is what I get there. Now I need to solve either angle A or C. To do that, I'm going to use the law of sines. Yeah, Tegan?
Yeah.
Okay.
I think you got an email or something.
I don't know, but you can go.
Okay.
I trust you.
It's for a ski race.
Oh, sure. Go ahead. That sounds familiar. So I'm going to solve for either angle A or C. Yes, Drake?
You have to solve for the smallest angle.
Yeah, so when I use the law of sines, I want to look for the smallest angle. So in this case, that would be which one, A or C?
Oh, that's not A.
A, because the side opposite A is smaller than the side opposite C. Okay, so I'll do sine of my newly discovered B over B equals sine of A over A. Cross multiply. Divide by 9. And then do the sine inverse of both sides. It's calculator time. So 4175 for this one. And then angle C, I can get quite easily just using the triangle sum theorem.
Okay, it's 2 times the 2 shortest angles minus cosine of the largest angle.
5098. Well, I mean, the law of cosines is just,
2 shortest sides.
it doesn't even have to be you don't have to do it that way,
Okay.
right? If you're doing like side angle side, it doesn't matter.
Right.
You can only do the one that you can do.
Yeah.
So just the opposite side and angle, the side by itself on the equal side is the same as the angle in the formula.
Okay, gotcha.
And then it's the other two fill in the other spots.
Okay.
You know what I mean? Like whether you put a squared plus b squared or b squared plus a squared doesn't
Well,
matter.
doesn't matter.
Or 2 times a times b or 2 times b times
Right.
a doesn't.
So 2 times those 2 smaller angles, and then
Sides.
it's 2 smaller sides, and then subtracted by cosine.
2 times the smaller side, 2 times each smaller side, and then times cosine of the opposite angle.
Okay.
Yep. And maybe I would say instead of smaller sides, other sides.
Other sides. Okay.
Right, because it's just whatever one you're isolating.
So like you can always isolate the biggest one, right?
In a side situation,
Yeah.
sure, because you have all 3 sides.
Okay.
Right? Like
Right.
you have enough information to solve for any of the angles.
Okay.
The deal is that you want to avoid possibly walking into an SSA 0, 1, or 2 triangle situation.
Okay.
And you can do that you can guarantee to do that by following
Okay.
finding the biggest angle with the law of cosines and then the smaller angle with the law of sines. And you can guarantee to avoid that, which is all that those rules are designed for, is just to avoid those SSA situations.
You won't get it wrong, it's just more.
Oh, you very possibly could get it wrong because you won't realize you're in an SSA situation and you'll find the wrong angle.
I got you.
Yeah, right. So you very likely will get it wrong if you don't do that. I want to be real clear. Like, it is very important that you're doing it that way, because then you don't have to worry about
Walking into a trap.
Yeah. Yes, for sure. Does that make sense, guys? Okay. Anybody else with questions from these problems?
Kind of good.
Yeah. It's one of these things, like, knowing what to do when is the hard part. Like, the actual calculations you're doing are pretty easy, especially compared to stuff we did first semester. And just making sure you've done enough problems to get the decision-making process down. Okay. Well, let's get through section 7.4. That's the last section for us. So here we're going to be looking at the areas of triangles. So if you guys went all the way back to your geometry class, what was the area formula you guys used to find the area of a triangle?
Oh, half BH.
Yeah, 1/2 base times height. Okay, so let's say I've drawn some arbitrary triangle like this, ABC. What sides, where is the base and the height?
So the base is would be B, and then lowercase b. And then the height is a straight line down from big B. And
Yeah. So again, the base doesn't really matter, right? So if you pick the base to be B, like Paul did here, the height then is this red line that we've drawn in. But I could have picked, say, side A to be the base, in which case then the height would be this line that comes in. Or I could have picked C to be the base, in which case the height is this green line that comes in. What's the problem with this, though? If you've solved for a triangle, what are you missing? The height, right? If I've solved for the triangle, I don't know what the height is.
gotcha.
So let's take a moment and adapt our formula here so that we can do this without having to solve for the height every time. So far, so good, right? We've just kind of drawn one example of what we can do there. Notice that this right here is a right triangle, correct? So I can say, for example, sine of A is equal to opposite over hypotenuse. Everybody agree with that? So to get the h by itself, I can multiply both sides by c. So my formula, 1/2 base times height, would now become A equals 1/2 BC sine A. And in that sort of situation, do I have everything I need if I've solved the triangle? Yeah, right? It's all just side lengths and angle measures. So we're good. We cool with that? So if I look here, I need side C, side B, and angle A. So really we'd be using this if I had a side angle side situation. Now what happens if I'm given like, angle, angle, side, or angle, side, angle, or something like that, or side, side, angle? What would I have to do then? Just solve the triangle enough so that I have some side, angle, side information, right? You just have to do enough so that you can plug the formula in. You don't have to solve the triangle completely because you probably don't need all of that stuff. You just, need an additional side or something somewhere.
It just builds upon the last chapter to solve.
Yeah, yep. Most of the time, I don't think you'll have to do any solving, but you might have to get the piece you're needing. There's another area formula that we can use called Heron's formula. So Heron's formula says the area of a triangle is equal to the square root of s times s minus a times s minus b times s minus c, where s is a plus b plus c all divided by 2. Sometimes we refer to s as the semi-perimeter, since a plus b plus c is the perimeter of our triangle. If I divide it by 2, it's like half of a perimeter. So like we called half a circle a semicircle. Same idea. Semi is the prefix for like a half.
Just trying to make sense of this. Why half?
Well, funny you ask, because the next thing we're going to do is kind of show you where this formula comes from.
Oh, fun.
So when we do something like this, like a proof like this, is this something I'd ever ask you to replicate? No. It's just kind of for enrichment. So it turns out that Heron's formula is just a version of that previous formula that we had come up with. And most of you should probably be like galloping goblins. I see no way how that was going to turn into that. But okay, I'll go along the ride with you, Mr. Kulik. All right, here we go. We ready? I'm going to start by multiplying both sides by 4. And then I'm going to square both sides. Now I notice here I have sine squared. If I think back to last semester, I know that sine squared is equal to 1 minus cosine squared. That was an identity that we used rather frequently. I'm going to use that substitution now. And then we'll distribute the 4a squared b squared through. And if I look here at the right-hand side of this equation, I notice that I really have is a difference of two squares. You guys see that? Not super obvious maybe at first glance that that was a difference of two squares, but when I rewrite it, you should be like, all right, Mr. Kulik, you got me. Definitely a difference of two squares. Oh, oops. Hold on. I don't want to do that factoring yet. I lied. Shoot. I was trying to do it without looking at my notes, and I missed this piece. All right. Here's the next piece. Does that look familiar? 2ab times cosine c. Hopefully, you'd recognize it as part of our law of cosines. So if I add that to the one side and then subtract c squared from the other side, I'm going to now make that substitution. My suspicion is this is not the proof that Heron used when he came up with this. This is probably a much later proof. But I don't think years.
Well, it had to be based on something.
I think that this was probably done geometrically originally.
Yeah. Yes.
Since the symbolic algebra was probably not refined when this is Heron, if it's the Heron that I'm suspecting, is an Egyptian.
Oh, okay.
Like a Greek by way of Egypt.
Yeah.
But so it's like BC's. Yeah. Which makes me think that this was probably done geometrically. Like this was a geometric proof, not an algebraic proof.
Like to draw pictures of words.
Well, they built the pyramids, so it's clear they had a pretty good understanding of geometry at that point. Okay. Now I'm going to do my difference of two squares. Everybody okay? I'm now going to get rid of the parentheses inside the other sets of parentheses and do a little bit of rearranging. So because the first set of parentheses, everything was positive in front, I can just kind of drop the parentheses and move things around, right? Here, though, I have to be a little bit careful. So I'm going to have a c squared and then minus ab minus 2ab plus b squared. Who recognizes this as something?
Oh.
Those are factorable. Those are perfect squares. So we'll factor those. Now guess what I see? That's a difference of 2 squares. And that's a difference of 2 squares. So I'll factor some more. And you're probably at this point be like, good Lord, Mr. Kulik, is this thing ever going to end?
I think you're an Egyptian.
Yeah. Well, I can walk like an Egyptian. That's a joke. It was a song in the 80s. That's okay. I didn't really expect anybody to get it.
Sorry.
You don't have to apologize. It's not your fault that you were born in, I don't know, 2005 or something. 4.
Are those supposed to be multiplication symbols of dot things, or are they subtraction?
These are subtractions. Yep. Okay. So now I'm going to just get rid of the parentheses inside the bigger sets of parentheses. Everybody so far so good? All right. So now what I'm going to do, I'm not going to do anything in that first set. And in the second set, I'm going to add in a plus C and a minus C. It's okay to do that because if I add C and then subtract C, it just did 0. So I didn't really do anything at all. And I'm going to do the same thing here in the second one by adding a B and then subtracting a B. And do the same thing in the third one by adding an A and then subtracting an A. So if I notice here now, in every parenthesis, I have an A plus B plus C. Everybody see that? If I go back to my Heron's formula, if I multiply S equals A plus B plus C over 2 by 2, A plus B plus C has to be 2S. You guys agree with that? Okay. So I have 2S, and then I have 2S minus 2C, and I have 2S minus 2B, and then 2S minus 2C. Oh, I'm sorry. Sorry. This is 2A at the end. Excuse me. Feel okay? If I look at each one of these parentheses, they all have a greatest common factor of 2. So I'm going to factor that out, that 2 out of each of them. Everybody agree with that? And since everything on the right-hand side of that equal sign is being multiplied together, I can multiply that stuff in any order I want. So 2 times 2 times 2, I'm going to multiply together to make 16. And then just change the order of the parentheses a little bit. I divide both sides by 16. And then we just square root both sides, and there we go. Well, that's what S is, right? That's just a shorthand, so we don't have to write all that gobbledygook in there.
Whoa.
Yeah.
Kind of just like math all over the place. It was like Yeah, this is how the entire thing went from like simplicity to complexity. It started like right here and then just like went up, and then just like crashed. Really
Yeah.
quick.
That's usually how an algebraic proof works, is it goes and it gets really messy, and then it all of a sudden gets cleans up, and it's like, oh, everything falls right into place, and everything cancels out, and and it's done. It's like, how satisfying is that? No, maybe not very. It was satisfying. It was satisfying for me.
When you had the twos and crossed them out to 16, I got so happy. I was like, yes.
Yeah, like that felt good, right?
Man.
All right.
So,
Yes.
is that equal to the equation you started with?
Yeah, they are equivalent statements. What's the difference between, or why would you want, or when would you want to use this Heron's formula? In a side situation, because the only inputs I need are the side lengths for the triangle. So that would let me avoid having to do any solving to get an angle measure to use the other formula.
Yeah.
It just shortcuts around one of those
Okay.
situations.
So when you multiply everything by 4, multiply. You didn't multiply A by 4, did you?
Well, I did this, right?
Right.
So these are just 4 things being multiplied together.
Okay.
So I just multiplied in any order I want. So I did the 4 and the 1/2 to make the 2.
Oh.
There's no distributing because there's no
Yeah.
addition and subtraction.
Gotcha.
You know what I mean?
You just cancel out on both sides because you switch it. Okay.
Does that make sense?
Yeah, I get it. Because you have, so either way, you kind of score the 16. Okay, I got you. Thank goodness you're not asking us to like repeat that.
No, would not ask you to repeat that. I would ask you to be able to follow along and understand what I did.
Yeah.
That I think is appropriate. So let's do a couple of numeric examples here. So let's find the area of the triangle where angle A is 43 degrees, or side B is 10, and side C is 27. Okay, what scenario are we in?
Oh, side angle side.
Okay, so that tells me I can go straight to my area formula. So I'll just type that in my calculator and I'm donezo's. What? Yeah, Mr. Kulik, that's it. Holy smokes, Mr. Kulik. That was wicked easy. Yeah, they don't all have to be hard. So what do we got? We got 9207 millimeters squared, since it's an area problem. That's it. One line of calculation, done. No fiddling around, no fooling around, straight to the matter.
I like it.
I like it. I like it a lot. What if we have this situation? Well, draw and label our triangle. What scenario are we in? Side, side, side. So I can dive straight into Heron's formula, right?
Yeah.
No!
Oh, come on.
What do I need to do first if it's a side, side, side
Check
situation?
as soon as possible.
I got to make sure it's even possible.
Yeah.
Mr. Kulik, would you be a sneaky jerk and do something like that to me? Absolutely. I'm not a sneaky jerk if I've told you that I would do it. I'm just sneaky then. If I don't tell you I would do something like that and then went ahead and did it, that's a sneaky jerk. If I tell you that I might do it, I'm just being sneaky now. Or maybe just being a jerk. I don't know. One or the other. But not both. Not both. Okay, so this is a possible triangle. So let's go ahead and apply Heron's formula. So I'm going to first start by calculating S, which is 23 over 2. So my area is the square root of 23 over 2 times 23 over 2 minus 5 times 23 over 2 minus 8 times 23 over 2 minus 10. So type this in my calculator. I'm going to do 23 over 2 first so that I can use the ants command and not have to type that in a bunch of, like a million times. And I get 1981.
Should I think it's something significant that happened? I can't really think about it because I was making 1981 job.
I was born. How's that for significant? Pretty shrug-worthy, I agree.
Well, I was laughing because he was asking for a joke and you're like, that's my birthday. So.
Well, birth year.
Okay.
You'll have to figure out my birthday some other time.
Gotcha. We have one piece of the puzzle. So.
Yes. The easiest piece.
Yeah.
Yeah, so that's basically it. The area problems just kind of boil down to using these two formulas. Either one of them is pretty easy to use as long as you're using in the correct context. So at this point, you could now finish the problem set, 23 through 30. But those are pretty straightforward problems. So I don't see that as more than like 20 or 30 minutes worth of problems if you're really kind of taking your time. If you're just kind of bulldozing, I mean, it's 10 minutes if you know what you're doing.
Gotcha.
Even if you're writing stuff down, so that's not bad. I want to point out one other thing I did in the content library, aside from like loading in stuff for all these upcoming chapters that we haven't done yet, is I put in this little
Saw that one actually. Yeah.
this little guy here. This is basically examples of things like the kinds of problems I would feel comfortable putting on like a homework quiz.
Okay.
So again, I have an example and I have the solutions. You can do this or not. It's not an assignment. It's just to give you an idea of like, hey, homework quiz, what kinds of questions would you be asking? Stuff like this, where I just ask you to solve a triangle and give you some information. I would give you the formulas for law of sines and cosines, but not like all the how to use it stuff. Just like, here's an example of a triangle and here's the letters and how the letters go. You know what I mean? Like sine A over A equals sine B over B equals sine C over C. I'd give you something like that, but I wouldn't give you in an SSA situation, you need to do this and this and this. Like that's the stuff that you guys need to remember. Okay. Yeah. So that's it for today, guys.